Hello, favorite class, and welcome to Lab 9. Lab 9 is all about identifying earthquakes. So, as always, make sure that you guys read the chapter, read the content. Um, we did earthquakes in lecture not too long ago, but you may have forgotten some of it too, so it might not hurt to go back and check your lecture notes. Make sure you reread some of that. The main part of the lab, and I think this is really cool. Again, I'm biased, right? I'm a little weird, but the main part of the lab, we're going to be trying to identify and figure out where an earthquake occurred. Um, to do that, you will need a compass, device for making circles. Maybe you guys used those before. I'm going to show you a way you can digitally do that if you don't have a compass. The video, I'm going to make a separate video. I'm going to add it on to the back of this one where I will show you how to do it digitally. All right. But I'll get you through everything in this physical real world video before I switch to that. Okay. So our assignment is 9, 2, 3, 4, 5, and 8. And really 9-4, this is the hardest part. If we can get through 9-4, everything else is easy, all right? So 9.2, we're down here. We're thinking about travel times for vehicles here. Talking about cars. Both cars use cruise control set at 1 mile per minute. 60 miles per hour, but the controls aren't exactly the same. Car 1 covers 1 mile in exactly 60 seconds, but car 2 takes 61 seconds. Because car 1 arrives a second before car 2 at each mile they travel, the delay between the arrival of car 1 and car 2 increases, right? So we have one car that is going 60 miles per hour and one car that takes 1 second longer, right? To get there, right? For reference, if you're going 60 miles per hour, right, in 1 hour, you'll have gone 60 miles, right? And then we can divide that by 60. So if you're going 60 miles per hour, you drive 1 mile per minute too, right? After 60 minutes, you would have gone 60 miles, right? And so this car is going just a little bit slower, right? Just 1 second slower it takes to get to the 1 mile mark, car number 2 here. In each of the boxes to the right of car 1 and 2, note the travel time in seconds needed to arrive at the milepost. And the boxes at the bottom of the figure indicate the delay time between the arrival of car 1 and car 2 at each milepost. Okay? So it introduces the question down here. We're going to flip to the next page. All right. So for 9.2 here, right? We've got car 1, car 2, we've got the delay, right? So it starts off, this car is going 1 mile every 60 seconds, this car is going 1 mile every 61 seconds, right? And so the delay then is going to be 1 second, right? So if they've both driven 1 mile, car 2 is going to be 1 second behind, right? Now, if they've driven another mile, right? Well, then how far back would car 2 be? Well, all we can do for this one, right, for car 1, we would just take 60 and multiply it by the number of miles. In this case, it's going to be 2 miles. 60 times 2, you might know this already. 120, right? For the next one, then we would take, for car 2, we would do 61 times 2, and this would get me 122, right? And we can fill that in. We have 120 here, 122 here, and now the delay, the time gap is going to be 2 seconds, right? So car 2 then would be 2 seconds behind, right? We can add our units in here. And keep doing this, right? 60 times 3, that's going to be 180. 61 times 3, that's going to be 183. Yeah, 183. And then there'd be 3 seconds behind, right? So as you can see, right, over time, right, this car is going to stay at its speed. This car is going to stay at its speed, but the time gap is going to increase between the two cars, right? Because one car is traveling slightly faster than the other one, right? So now, once we filled in this, we can jump down here using the information. How far do the two cars travel if car 2 passed the street light? So there is a street light here. It talks about using the information. How far do the two cars travel if car 2 passed the street light? 25 seconds. If car 2 passed the street light 25 seconds after car 1. Well, think about it, right? Every mile they travel, right, there's a second being added onto it, right? So if it's 25 seconds, right, think about how many miles it would take for that gap to be 25 seconds. And then what about 45 seconds, okay? For D, now determine the precise time that the cars started their trip. So we're kind of working backwards. We know when the cars pass by us, but we want to know when the cars started, right? Like, let's say you lived, I don't know, an hour away from me, right? And you show up to my house at 4 p.m. coming over for the party, right? that would have meant that you left your house at around 3 p.m., right? Well, it doesn't work any other way, right? So we want to determine the precise time that the car started their trip, hours, minutes, and seconds, if car 1 passed the street light at 12:25, right? So 12:25. And this is our seconds. This is going to be our minutes. This is going to be our hours, right? Now we're saying 25 seconds before car 2. So there's a 25-second gap before car 2 gets there. So that must mean that they have, right, if there's 25 seconds between them, they must have driven 25 miles, right? And we know that it takes car 1, so 1 minute to drive 1 mile, right? So in this case, we would take 12:25 minus 25 miles, right? And that would mean that the car 1 has left exactly at noon, right? What about 45 seconds then, right? So how would you go with that? Figuring out about that, right? So for this one, we know this would have had to have left exactly at 12 noon. Okay, it doesn't specify AM or PM here. Let me double check it. Determine the precise time. If car 1 passed the street light and was 25 seconds before. Yeah, so that makes sense. So if car 1 arrives at precisely 1:40:22, followed by car 2 at 1:46:37, how far do they travel in miles? Well, we want to figure out the time gap between these two. So how many minutes and seconds are there between those two cars, right? From that, we can figure out the miles. So let's say it's 30 seconds of difference, right? If there's 30 seconds of difference, we know that it's got to be 30 miles, right? And then from there, we can reverse, we can work backwards again, kind of like we did up here. We can look at, okay, well, it's 1:45:22 when car 1 arrived, and there's a 30 mile gap, which means a 30-minute gap, right? And then we can subtract, 30 minutes from this, for example, to figure out then exactly when the cars left, okay? I'm not giving you guys the answer for this, but I'm helping you kind of set it up, right? So figure out the time between these two and the number of minutes and seconds. Figure out the total number of seconds. That's going to give you the total number of miles, which will give you then, right, the delay is equal to the miles here, right? And then you can figure out, okay, if it's 30 miles, we would subtract 30 from our minute section, right? And that would tell us when it left, okay? Hopefully that makes sense for 9.2. As always, let me know if you have any questions. Moving on to the next part here, this is 9.3. For this one, we are looking at a travel time diagram. So we're looking at this graph up here. Let me get my index card for this. Or just some scrap paper. Perfect. Sorry, I'm a little sneezy right now. I'm trying to sniffle too much. 1 second, guys. Okay, we're so back. All right, so we're going to be looking at this graph again up here. On the y-axis here, we have seismic wave travel time in minutes. And then down here, we have the distance from the epicenter. And some students kind of look at this initially. Sometimes they get confused. But the fastest waves are actually going to be the ones down here. Some students think that the wave going up this way is going to be the fastest. That is, that's not the case, right? Think about it, right? Look at 5 minutes, right? At 5 minutes, this wave has only gone 1,000 kilometers. This wave has gone a little bit more. This wave's gone a little bit more, but then over here, right, this wave, the P wave, has gone over 2,000, closer to 3,000 kilometers. In the same amount of time, these guys have just barely made it to 1,000, right? So the faster waves are going to be down here, and the slower waves are going to be up here. Okay? Refer to the travel time diagram in 9.6 to answer the questions. How long does it take a P wave to travel 5,000 kilometers? So we want to go to distance from epicenter, 5,000, right? We come up here. Take our straight edge, take our piece of paper, we'll put it right here, come straight across to right here. That's 5, so it's a 6, 7, 8, about 8.5 roughly, I would say, about 8.5 minutes. This would be 9.3, question A, about 8.5 minutes or so. Okay. That's what we're doing for the rest of them. So how long does it take for the S wave to travel 5,000? How long does it take for the L wave? How long does it take for the R wave? Okay. Hopefully not too bad, right? We have a great example right there. So that is 9.3. Let's get to the real, the meat and potatoes, as they sometimes say, of this lab, which is 9.4, right? Don't be intimidated, guys. You can do it. So it's giving us a bunch of information, some background tools. This is the general steps that we're going to be using for 9.4 to try and figure out and locate where the earthquake occurred. We have our seismogram down here. We're going to be looking at seismograms, so it tells us how to read a seismogram. This kind of wiggle right here, this is the background noise. There's always a little bit of background noise in the earth. There's always something moving on the earth, and we can pick that up sometimes. But this right here is the first wave. If you guys remember the earthquakes lecture, the P wave is always the first wave. P wave for primary wave or pressure wave. Always the first wave. So this is the first wave that we record. And then there's a gap, and then there's the second wave, which is called the S wave, right? This is kind of like our cars, right? We have one car that travels a little bit faster and then one car that travels a little bit slower. And what we're going to do is we're going to use the gap basically between these waves, the time gap between these waves, and we can figure out how far away the earthquake was. And then by looking at a couple of those, we can actually find out how far away the earthquake was and where exactly it happened too, which is kind of cool. Okay, so this is giving you background information on this page. Over here, then, we want to use the figure above to determine the arrival times of each of the 4 different types of waves. Place a P next to the place where you believe the P wave arrives, an S where the S wave arrives, an L where the L wave arrives, so on and so forth, right? And so if we look right here, right, it's all background noise, right? Each one of these is giving, these lines represent 1 minute. This is 105, 106, this would be 107. Down here, this is 142. This would be, I'm assuming they're supposed to be pointing here, 218. This would be 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and this would be 35. So that's interesting. 235 is right where we start to see this happen. We see our P wave. Let's follow the instructions as best as we can. We want to look at right where this first little divot is, and it's just after 235, just a little bit after, if not right on there, yeah. Did they zoom in? They don't zoom in here for us. They zoom in for this one, but we'll say, yeah, for the P wave, right? P wave would be about 235. We don't know if it's AM or PM, it's fine. 235. Then we want to figure out the S wave, so they did zoom in there for us, right? The S wave, right, this would be 35, 36, 37, 38, 39, and then a little bit after this might be, I don't know. This would be half. So maybe 2, what do we say, 39? We said 239. And I would say about 15 seconds. 15, something like that. 239.15 for our S wave, all right? I'll let you guys figure out the L wave and the R wave. These guys are a little bit trickier because it gets a bit more jumbled up in here. But trying to identify where the L wave is, trying to identify where the R wave is. Looking at the amplitude of the waves recorded on the seismogram, which wave type do you think might cause the most damage? Yeah, so what do you think? Which wave out of all 4 of these, we have our P wave, S wave, L, and R waves, is going to cause the most damage? And then why? Why do you think that? Is it the first one? Is it the last one? Is it the smallest one? The biggest one? The widest one? You tell me. All right, that's what we're doing here. This is kind of a practice for what we're getting into for 9.4. All right. Then we come to the actual seismographs of interest, which are on this page. We have Seattle, Washington, we have Austin, Texas, and we have Chicago. What we're going to be doing then is we're going to be identifying the P wave arrival times for the 3 cities. We're going to identify the S wave arrival times for the 3 cities. And then we want to figure out the S minus P delay for those cities. All right. You guys, this is why you're watching the video, hopefully. You can skip the L and the R waves, and you can also skip down here the L minus S and the R minus L. All right, we don't really care about that. It's a lot of busy work, and 9.4 is already pretty big. All right, so you guys can skip this part and you can skip this part, but we do need to do S and P. We do need to do P and S up here. Okay, so I'm gonna be a little biased. I'm gonna do my hometown. I'm gonna do Chicago. All right. Typically, we don't get earthquakes in Chicago, but we can measure them, even if they're on the other side of the planet or somewhere else in the country, all right? We can measure them basically anywhere if they're big enough. So what we want to do is for Chicago, we want to look at the P wave. When does the P wave get here, right? Here is our background noise, right? And then all of a sudden, boom, right? We've got our earthquake here. They're telling us this is 1400, so that'd be 2 p.m. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just counting the minutes. This would be 10. So somewhere around 1409. Around 1409. Can't write. 1409. We're entering into the P wave zone, right? And it's not halfway. I would say it's maybe closer to 3. It's tough. It does drop down here. I think that's kind of, yeah, we'll say halfway. I'll say halfway. I like that. So we'll say 1409 and 30 seconds for, this is Chicago here we're doing. And this is our P wave, right? You guys see that? So I just counted. This is 1400 or 2 p.m. basically, and then each one of these lines is 1 minute of time. So 1401, 1402, 3, 4, 5, 6, 7, 8. You get to here 9, and then our P wave arrives right around halfway, right? Halfway between the two. Then we want to figure out the next one, which is going to be our S wave here, right? S wave, and so yeah, okay. Here's our P wave, and we got that pressure wave. It kind of slows down, dies down, and then we see another big jump right around here. So this was 1409. This would be 10, 11, 12, 13, 14. Look at that, 14, 14. 14, 14. How many seconds then? I think it's closer to this side, so I'm going to say 14 minutes and 15 seconds for the last part here. So this would be 2:14 and 15 seconds for our S wave, right? So then what we want to do is we want to take the S wave time minus the P wave time to figure out how much time is between those two seismic waves, okay? So I've got 14, 14, and 15, and then I've got 1409 and 30. Now we're working with hours and minutes and seconds, so you can't just do a straight subtraction because this is base 60, whereas most of the numbers that we deal with are base 10. And so what we're going to do is we're going to do 14... 15 minus 930, right? So we have one wave arrives. The S wave gets here at 1415, right? The P wave gets here at 930. We're just doing, as it says, S minus P, right? So we're subtracting this one from this one. When I do this, 15 minus 30, I can't do that. I have to cancel this, right? This goes to 13 up here. And I don't add 10, I add 60, right? So this becomes 75. So 1375. Now I can subtract 30 from 75. Gosh, math. That's 45 seconds, right? And then 13 minus 9. That's 4. I'm not a math major, guys. But we get 4 minutes and 45 seconds. That is our S minus P for, this is Chicago again. Okay. So we know that there are 4 minutes and 45 seconds of time between when the P wave arrived at our seismic station and when the S wave arrived at our seismic station. Okay? That makes sense? That's for Chicago. You guys will have to do Seattle and you guys will have to do Washington, all right? But you can follow my example, figure out exactly what time they get here. Here's the P wave for Austin. Here's the P wave for Seattle. And it looks like our S wave would be right here and right here. Okay? All right. Let's move on to the next page then, all right? So for the next page, here's the same graph from 9.3. So this is our graph that, again, shows basically the speed of our waves. So we have distance again on the x-axis. We have the travel time again on the y-axis here. Slide the station worksheet across the travel time diagram until all 4 arrows coincide. We're not going to do. We just need to do the P and the S, right? What the heck? What is this square thing going on? Okay. This is probably the trickiest part of this whole operation is we want to figure out the time, right, between the P wave and the S wave, right? We did figure that out. We want to figure out now the distance. So we can actually figure out that distance. It's very similar to the cars back here, right? We know that the P wave is always going to be faster. So the P wave is kind of like car 1. And the S wave is always going to be slower. It's kind of like car 2, right? And we can use that time difference and we can figure out how far away the earthquake was from Chicago, okay? So now we're going to take our piece of paper. I just got a regular index card here. You can use that. You can use a regular scrap paper if you want to. But what I'm going to do is I'm going to move my book a little bit. I want to make sure you guys can still see because I want to access this side of the graph here. I'll put my paper, my index card right here. So this is 0 minutes down here. I know this is 5, and I said what, 45? So it's going to be tight. Here's 30. I'm going to put another dot right here, right? So between these 2 points right now, this is 4 minutes and 45 seconds, right? Which is the time, right, for the time for the S minus P for Chicago from over here, right? So I've got 4 minutes and 45 seconds of time right here. Now what I want to do is I want to figure out where on this graph there's 4 minutes and 45 seconds of time between the P wave and the S wave, okay? So what I'm going to do, use 2 hands for this, I'm going to slide this paper up the graph, and I'm waiting. I'm keeping my paper vertical, keeping this straight up and down. I'm not going like this. No, don't do that. Don't do that. All right. I'm going to slide it up the graph just like this, trying to keep it nice and straight, nice and vertical. Oh, and come back a little bit. Maybe we go up a little bit higher. Ooh, we're getting close, guys. Oh, I like that. I'm going to say like right here, okay? So right here, if you look, I'll move my hand, there's 4 minutes and 45 seconds of time between the S wave and the P wave right where my index card is, right? Because here's the S wave here, here's the P wave here, there's my little dots right there. And I'm going to make a very, JS writing in his book all of a sudden, but I'll make a very, very faint pencil mark right there, okay? So, again, right? Mark off the amount of time, so 4 minutes and 45 seconds for Chicago. We slide it up the graph, keep the card nice straight up and down until both dots touch. This is going to be our P, right? This is going to be our S up here until both dots touch. Yeah, I would say right around there. It looks pretty good. So in this case, I make a mark so I know that the earthquake occurred this far away from Chicago. So I'm going to say for Chicago, I'll move my paper back over here. I'm going to say for Chicago that it was what? It's a little over 3,000? I'm going to say like 3,025 kilometers is the distance the earthquake was from Chicago. One thing you don't want to do is you don't want to just go up to 445 and then come across and then see where it hits. You're gonna be off by a couple hundred kilometers if you do that. So you do have to take a piece of paper, or I guess you could do it digitally too, but you want to slide it up the graph here to figure out your distances. Might actually be easier digitally. Like you could make a line segment that's 4 minutes and 40. Like take a screenshot, make a line segment that's 4 minutes 45 seconds, and then just like slide that. Keep that automatically stay straight up and down. Right, just drag it over until both ends of the line segment touch. So might actually be easier digitally. All right. But we know that the earthquake is this far away then from Chicago, about 3,025 kilometers or so. All right. You guys, again, will have to do Seattle and you'll have to do Austin. Okay. So now we're still at 9.4. I told you guys this was the hardest one, right? We're still at 9.4. So now what we want to do is we want to try and figure out then where did the earthquake actually occur? Okay. If I told you that I lived, 10 miles from San Jac, would you know where I lived? Hopefully not, unless you're a creeper, right? Hopefully not, right? You would know though that I lived, in a circle 10 kilometers around, San Jac, right? Same thing is true here. We know that the earthquake was 3,025 kilometers away from Chicago, but we don't know is that north, south, east, where, we don't know where that is, right? So all we can do is we can draw a circle basically around Chicago that's 3,025 kilometers in length, okay? What we can then do is we can draw circles for the other cities that you guys are going to figure out for like Seattle and Austin. And where all three of those circles intersect and overlap, that's going to be where the earthquake occurred. So in this example up here, right, we've got 3 different seismic stations. We've got one up here, and this is, what is that, Newfoundland, I think, Canada. We've got a station down here, looks like, I don't know, Venezuela. We've got a station up here in, I think, Alberta, British Columbia, Canada. And they draw circles, right? So for this station, they know it's 2,000 kilometers away. They draw a circle around this station. For this one, they know it's 4,000 kilometers away. And for this one, they know it's 6,000. And the point where all 3 circles intersect and overlap, that is the epicenter. So in this example, this is where the earthquake occurred. That's what we're going to be doing. So if you have a compass, then what you would want to do, I don't have my compass with me, so I'm going to cut the video at the end here. I'm going to show you guys the digital version, but basically you're going to set your compass to 3,025 kilometers, something like that. And then you would draw a circle then around Chicago You basically draw a circle then around Chicago that's 3,025 kilometers. You have to use a real circle. Don't freehand it. Oh, it drives me nuts. All right. Again, I'm gonna put the I'm gonna cut the video. I'll show you guys the digital way to do this. But there's an easy way you can do this in PowerPoint. You can make circles easily. Okay. All right, we are digital here. So we are using Microsoft PowerPoint. That is one of the applications that you guys should have access to through the college. I think there's a web app you can use too if you don't have it on your computer. I have it installed on my computer. I am using a Mac right now, so it might look a little bit different if you are on Windows, but it should be pretty similar. Okay, we've got our map though of the different cities, and we're trying to figure out then where the earthquake occurred. If you have a compass and paper, you can use that, but I'm going to show you guys the digital trick, kind of the digital way to do it. So we know from the example that I was doing, right, that Chicago is 3,025 kilometers away from the earthquake. Again, we don't know if it's north, south, east, or west, so we got to draw a 3,025 kilometer circle around Chicago, basically. So what we're going to do is we're going to go to I'm at home right here. I'm going to click on shapes. Your first inclination might be to use the circle shape, but we want to use, if you come down here, it's under flowchart. It's a circle, but it's got crosshairs in it. All right, so we're going to use this one right here. All right, what we're going to do then is we're going to put our cursor on the scale bar here, and we're going to draw our circle. Notice that it's kind of goofy, but if I hold down Shift, it locks it to be a nice precise circle. Okay, so we're going to do that. All right, it's a little unwieldy, bear with me here. We're going to do change the fill. We don't want any fill, and then make the line color something that's not black. So I'm going to use purple. Why not? I'm going to drag this then onto my scale bar here. Okay, you guys see that? The circle itself, the center point has to be 3,025 kilometers away. So it can't just be the circle. We want to take this though and extend it hold down Shift. Hold on. Extend this way. We'll extend it this way. Yeah, that should work. That should be 3,100. I'm going to recenter my circle, putting it right there. So each one, this is 3,000, this line right here, right? This is 4,000. Each one of these big ones, this would be 2, 4, 6, 8. So this would be 3,200, 3,400, 600. These smaller ones then are 100. So then halfway between this and this would be 50, and then 25 would be right there. So I'm going to reposition my circle that I'm trying to draw back on my graph right here. I'm at 3,100, so I need to make it just a little bit smaller, right? It's fine if it comes up like this because it's still on the far left. It's still right on the line. That's going to be about 3,025 right there, give or take. Make it a little bit smaller maybe, okay? So what we can do is, I'm going to zoom out here a bit. Okay. We can then take this and we can place this dot right on Chicago, okay? And then we can then take the other. So once you figure out the distances for the other cities, and I believe the other cities should be a little bit smaller circles than Chicago. I think Chicago is the biggest one in this example here. Let me double check real quick. Yeah, Seattle should be pretty close. Austin's going to be closer than Chicago. Yeah, so Chicago's the biggest one. We've got our circle essentially, right? And so you can just repeat this process then for the other two cities. So this is an example now. We're entering into fake territory. This is accurate, as you can see right here. The earthquake is somewhere along the circle right here, but we can copy and paste this circle now. We can make it smaller. Maybe Austin is hypothetically what? Maybe Austin is like 2,000 kilometers away. We would put this circle here then on Austin, right? And then we would do Seattle, right? So we put it again, make a third circle here. We can shrink this down. Seattle's going to be closer. It's probably not going to work because I'm just making it up here. But we'll place 3 circles. We'll place 3 circles. And wherever all 3 intersect and overlap or get very close, that'll work for this one. That would be where the earthquake is. So in this example here, where all 3 circles, the curved lines intersect, would be right here. So kind of off the southern coast of California, okay? That's about all. That's what we would say in this example, right? Seattle is not right. Austin's not right. I just made those numbers up, right? But that's how you would locate the epicenter, is figure out where all three circles either touch or get very, very close. Okay? I hope that helps you guys. Let me know if you have any questions, and we'll jump back to the book. So we will come back to that in a second here. In the meantime, though, we did 9.4. There's a few more questions still. Let's see here. When exactly did the earthquake occur? And don't worry about this. You can skip here. You can skip E also. All right. So skip 9.4E. All right. Skip 9.4E. Okay. Let's move on. 9.5. 9.5 here. We're in the home stretch, guys. This one is not too difficult. We're measuring the magnitude of the earthquake. So magnitude, right, basically measures the amount of energy that an earthquake produces when it goes off. It's usually the number you'll hear in the news. So, like a 9.0 or an 8.1 or 6.2, right? That's going to be our magnitude. How do we figure that out? Well, there's digital tools, but we have our lovely graph down here that we can use to figure that out with, okay? So for A, what is the magnitude, the moment magnitude for an earthquake with exactly the same P wave amplitude as the example in the chart below, but with an SP delay of 30 seconds? So what you want to do for this one is take a ruler, take a straight edge. I got a piece of paper here. It says, all right, magnitude, exactly the same wave amplitude. So our wave amplitude stays the same as the example, so we're going to use this point. We put our ruler on this point, and then, what does it say? With an SP delay of 30 seconds. Then we bring it over here. We put it right here, and then we draw a line across. I'm going to put it right here, a very faint line in my book. So it's just above a 4.5. I would say maybe 4.6 would be the magnitude for this one, all right? Then you want to do the same thing, but you want to, again, keep it on this. For the first one, we're keeping it on this dot, keeping the amplitude the same. But now it's for 10 seconds. So then we want to pull our straight edge down here. We're going to draw another line across. And then wherever it crosses right here, that's going to be your magnitude. All right. So answer the second half of this one. This one's about 4.6 is the example I'm giving you. Figure out that one, though. What is the relationship among wave amplitude, magnitude, and distance, right? So think about it, right? As this goes up, what does this do? As this goes down, what does this do, right? Think about that. What is the magnitude for earthquakes? Now you're looking at the same SP delay, but with different amplitudes. So you're going to put your card on this one, and you're going to move it up and down on this side, okay? You're going to slide your card up and down. The first one is what? Over here with 2 millimeters. That's down here quite a bit, right? So you're going to draw a line here, figure out the where it crosses in the middle, and then at 100, right, you're going to draw another line, figure out that one. Okay, I think you guys can do this. Then figure out the magnitude then for this earthquake based on the 3 stations. Okay, and the last one is 9.8. I have pictures of this in my earthquake lecture. The ground liquefied in these buildings. They didn't crumble. The ground turned to soup like quicksand, and these buildings just sank into the ground. Pretty crazy, pretty wild. But the last one here is about tsunamis. All right, tsunamis are really, really dangerous. So if you guys ever experience an earthquake and you're at the beach, please go to high ground. A lot of times, sometimes there was a big one in 2004 that killed over 200,000 people. But there was a little kid, and she just learned about tsunamis, and she told her parents, "We need to leave now." All the water was draining off the beach, and people were going out to explore. "Oh, look, there's fish flop." No, oh my gosh, don't do that. So if you're ever at the beach and there's an earthquake, go to high ground, guys. All right. But anyways, let's talk about math. 9.8. Why is a tsunami so powerful? A cube of water, 1 foot on a side, weighs approximately 62 pounds. Imagine being hit by a 62-pound weight. You're right. That would very much hurt. So now imagine a low wall of water, 10 feet wide, 1 foot deep, and 1 foot high. It would weigh how much? Well, we know that, right, one of these is 62 pounds, right? So now it's 10 feet wide, 1 foot deep, and 1 foot high. So we would do for A, right, it would be 62 times 10, right? And so that's going to be 620 pounds. That is probably heavier than any person, right? Any person for the most part, right? That's a lot of heft, right? Now, a wall of water 30 feet high, like the Sendai tsunami, 1 foot deep and 10 feet wide. So we can recalculate it if we want, but we can just take this number now. We're going to multiply it by 30, right? Yeah, because it's 10. Now we're doing it by 30. So 620 then times for B, right? Be 620 times 30, right? That's going to give you your answer. So on and so forth. You can keep building off of these to get to the other ones, right? I don't know if you've ever seen like videos like on the internet, like people like driving through floodwaters. Like sometimes they don't make it, right. Their car gets washed away because the force of the water is incredible. They always say in Houston, right, like turn around, don't drown. Yeah, because that fast moving water can easily push like even a big heavy truck, a big heavy vehicle. And yeah, people inside of it, it's not the best for them, right? Hopefully they make it, but there's a lot of force behind moving water, and tsunamis are a great example of that. Okay, yeah, the simple calculation to help you understand why just water can cause so much damage, right? What does it say? A little rain never hurt anyone, but a lot could kill you, right? So we want to be safe around water, and especially if there's an earthquake and a tsunami. All right. But if you guys have any questions at all, again, please let me know. Hopefully that gets you going on 9.8. Yeah. Let me know if you guys have any questions or concerns. Always happy to help. Have a good one.